Hello, welcome to lecture 12 for Math 155. Today we're going to be continuing our exploration of functions of multiple variables by looking at how we can take derivatives in an arbitrary direction. This is known as a directional derivatives. It's one of the new key terminologies for today. We're also going to be talking about how this relates to something called the gradient vector and what that represents. Okay, so let's dive in. So previously we talked about how we take a partial derivative of a function, which tells us about the rate of change in the direction of a coordinate axis. So df dx, for example, of a function f of xy, df dx tells us about the rate of change of that function as we move in the direction of the x coordinate axis. And likewise, if we took df dy, that would be the rate of change of our function if we move in the y-axis. But how about if we want to move in an arbitrary direction, as shown in this diagram here? For example, if we want to move a little bit in the x direction, but also a little bit in the y direction, how do we work out what the derivative is of a function in that case? This is related to another problem where if we are, say, standing on Burnaby Mountain and we want to find out what is the direction of steepest ascent, how do we do that? In more general terms, if we have a function which describes a surface, how do we work out which is the fastest or maximum rate of change of that function at a particular point? So in this case here, if we zoom in, if say we were stood at this point here, which direction should we go in to have the direction of steepest ascent up this hill? Well, intuitively, usually we tend to walk in switchbacks to make things easier. So we're sticking quite close to our level curves. But if we want to go in make things hard, go in the direction of steepest ascent, we should be going away at right angles to our level curves. So our direction of steepest ascent in this case should look something like this. And we'll talk about why we should be going at right angles to our level curves a little bit later on. Okay, so the first new piece of terminology we're going to be meeting today is something called the gradient vector. Now, the gradient vector is simply a vector composed of the partial derivatives of our function. So if we have a function of two variables, x and y, then our gradient vector is going to have two components. And it's given by this symbol here, which is an upside down triangle with a vector arrow above it, and can be read as gradient or sometimes simply just grad. So grad of f of xy is going to be the partial with respect to x and the partial with respect to y, as it written as a vector. We can also write this as df dx, df dy, those are the same things. Okay, so if we go through an example of what this is, suppose we have a function f of xy is equal to x e to the xy, and we want to find the gradient of f. Well, first thing, we just work out our grad of f of xy is a partial with respect to x, a partial with respect to y. So the partial with respect to x in this case is e to the xy plus x times by y e to the xy. And the partial with respect to y is x squared e to the xy. So that's simply it. We just take our partial derivatives and put them in a vector. The second part of this example says find the gradient at the point 1, 0. So all we need to do is substitute in x is equal to 1 and y is equal to 0, into what we found just now. So grad of f at 1, 0 is equal to, well, let's substitute in x is equal to 1, y is equal to 0. So we get e to the 1 times by 0 plus 1 times by 0 times by e to the 1 times by 0. Our second component is 1 squared times by e to the 1 times by 0. So this is just going to be 1, 1. So this tells us that the gradient of our function at the point 1, 0 is 1, 1. We'll talk about what that means a little bit more later on. Okay, so the next thing we're going to be talking about is something called the directional derivative. Before we do so, let's just recall what we talked about in terms of linearization of a function. So suppose we've got some function f of xy, and if we want to plot this as a surface, then z is the height of that surface above the xy plane. And we can linearize that function at a point x0, y0 And all that's saying is if we take the height of our function, our z value at x0, y0, we can move a little bit away from that in either the x or the y direction, or in both of the x and y directions, and we can approximate the value of our function at that point using this linear approximation. Okay, so what this is really saying here is we've got here x minus x0 is the change, the delta in our x values, and here in the y direction, we've got the change in our y values, and the partials are telling us the rate of change in each of those directions. Partial with respect to x is telling us the rate of change in the x direction, and the partial with respect to y is telling us about the rate of change in the y direction. So this first part here is telling us the total change in our function height in the x direction, and likewise the second term here, or the third term in the function, the second partial term here, is going to be the change in f in the y direction. If we take both of these together, this gives us the total change in f. If we move a little bit in the x direction, a little bit in the y direction. So what's this got to do with directional derivatives? Well, the directional derivative of a function at a point in the direction of a unit vector, so a vector of length 1, we'll call this just some general unit vector AB. We say this, the directional derivative given by this d subscript u, our function at x0, y0, is simply equal to our partial with respect to x evaluated at x0, y0 times by a, where a is the first component of our unit vector u, and then our partial with respect to y, again evaluated at x0, y0, multiplied by the component, the second component of our unit vector u. And this is very similar to what we had up here, right? We've got our partial times by our delta x, where our delta x down here has been replaced by an a. And then we've got this being added to our partial with respect to y, multiplied by b. So the b here corresponds to the y minus y0 up here. So these two things are very closely related. And we see as well that this is essentially just a dot product. We've already talked about our gradient vector, which if you recall from above, our gradient vector is just the vector composed of the partial derivatives of our function. So we can write our directional derivative as our gradient vector evaluated at x0, y0, dotted with our unit vector u. So if we visualize what's going on here, we imagine we've got our xy plane here, we've got some x0 and y0 values, these could be anything. And what we're saying is, okay, well, if we take our partial derivatives, we're looking at what happens if we move in either the x direction or in the y direction. But now we want to move in an arbitrary direction. So let's call this arbitrary direction u, which is a unit vector. In other words, we're going to be moving a units in the x direction, b units in the y direction, but the length of this vector is 1 because it's a unit vector. So this u could point in any direction. We're saying what is the derivative of our function, the directional derivative in that direction there. Okay, so let's work out an example here. If we've got a function fxy is equal to x squared minus y squared, first find the gradient of f and then find the directional derivative of f at 2, 1 in the direction of v, which is a vector equal to 1, 1. Okay, so first of all, let's find grad f. So this is going to be our gradient vector composed of our partial derivatives. And so if we take the partial derivative with respect to x, we get 2x, and the partial derivative with respect to y is minus 2y. And then if we substitute in our values, x is equal to 2, y is equal to 1, grad f at 2, 1 is just going to be 4 minus 2. Now we want to work out our directional derivative in this direction here, but note that this is not a unit vector. We needed to have a unit vector. Recall up here in our definition that u must be a unit vector. So the first thing we need to do is convert this v into a unit vector. So let's say that u equal v over the length of v. So this gives us a unit vector u. Now the length of v is going to be root 2. So this is just going to be 1 over root 2, 1 over root 2. So that's just the unit vector in the same direction as v. And then to work out our directional derivative, d subscript u, f at 2, 1. We just take the dot product of this, our gradient, evaluated at 2, 1, and our unit vector here. So we just take the dot product of these two things here. So we have grad f at 2, 1 dotted with u. So if we substitute those in, we have 4 minus 2 dotted with 1 over root 2, 1 over root 2, which simplifies down eventually to be root 2. So that here tells us that for every unit step we take in this direction here, in the direction of this vector 1, 1, when we are at our function given by xy coordinates 2, 1, every step we take in that 1, 1 direction, from that point, our function value, our height of our function, increases by root 2. So this is what our directional derivative is telling us. It's essentially a generalization of what we do with our partial derivatives, where we move along our coordinate axes, but now we're just moving in an arbitrary direction. Okay, so let's talk a little bit about some geometric facts related to the gradient. So a gradient vector points in the direction of steepest change, or the steepest ascent, and also the gradient vector is orthogonal to the level curves of f. So let's talk about why those things are the case. So first of all, let's think about the direction of steepest ascent. So if we say let u be direction of steepest ascent, and the maximum change in our function is where our directional derivative, so du of fab, is biggest. Now, if we recall, we can write down du of function at ab is just the dot product of the gradient of our function at ab with u. If you go back to our notes on the dot product, if you recall, we can also write that any two vectors dotted together, we can write as the length of our first vector, so the length of our grad of fab, multiplied by the length of our second vector, in this case the length of u, times by the cosine of the angle between them. So this is just from our rules about dot product. But we know that we've got a unit vector here. By definition, u is a unit vector. So the length of u is always equal to 1. And this grad here, this length of this gradient vector, this is also fixed. So the only thing that we have that we can vary is this cos theta. And so cos theta is largest when theta is equal to 0. So when cos theta is equal to 1 or theta is equal to 0, this is when our gradient vector is going to be, our directional derivative, sorry, is going to be largest. So this means that our directional derivative is maximized when u is in the same direction as our gradient vector. Okay, so write down therefore du of fab is maximized when u is same direction as gradient. Okay, so that tells us that our gradient vector always points in the direction of steepest change. How about the second part, the fact that our gradient vector is orthogonal to the level curve? So that, in other words, if we look on this diagram to the right, we have right angles here, and this is saying that our gradient vector always points in these directions here. It's always orthogonal at right angles to our level curves. Okay, so let's think about this diagram here over here on the right, and let's say let K be called fxy, be a level curve. And AB a point on that curve. And we can think about a point that's nearby also on the level curve. So let's say let x, y, let's call it x1, y1 actually. x1, y1 be a nearby point on the level curve. So we're going to say there's a point here, x1, y1, and we can think about a vector. I'll zoom in here. This little arrow here, I'll do it in a different color. So we can think about this vector here, v, which goes from AB to x1, y1, some other point on our level curve that's very close by. So if we think about our linear approximation, our function value at x1, y1 is going to be approximately equal to our function value at AB plus the derivative in the x direction times by x1 minus a plus the derivative in the y direction times by y1 minus b. And because we're going to be taking these points AB and x1, y1 on our level curve, these things being the same, we can also, because we can choose an arbitrary point as close as we want, we can turn this into an equal sign. So we end up with 0 is equal to our partial with respect to x times by x1 minus a plus our partial with respect to y times by y1 minus b. The sum of those two things is equal to 0. And this, though, is just our grad of f at AB dotted with our vector v. So this vector v we've defined here is just the vector from AB to x1, y1. So if the dot product of these things is 0, that means that our gradient of f at a point on this level curve is perpendicular to a level curve. Okay, so you don't need to memorize the proofs that I've just gone through. They are just designed to give you some intuition as to what's going on, what it means to have a gradient vector and why it is pointing in the direction of steepest ascent for your function, also why it's orthogonal to the level curves. Okay, let's go through an example here. So we've got a function fxy is equal to x squared y plus y squared. In what direction does fxy increase most rapidly at 1, 1? So at the point x is equal to 1, y is equal to 1. And what is the rate of change of f in this direction? Okay, so suppose we have our function. So fxy is equal to x squared y plus y squared. So grad of f of xy is just going to be our partials. So we have 2xy and x squared plus 2y. And if we look at this at the point 1, 1, simplifies down to be 2, 3. Okay, so this tells us, because we already know from the previous slide, that our gradient vector points in the direction of steepest ascent, that in the 2, 3 direction, f increases most rapidly. And how do we work out the maximum rate of change? The maximum rate of change is just given by the length of our gradient vector. So if we work out the length of grad f at 1, 1, this is just going to be Pythagoras square root of 2 squared plus 3 squared, so the components of our gradient vector, which just turns out to be root 13. That tells me that for every step I take in the 2, 3 direction, every unit step I take in the 2, 3 direction, I end up increasing my function value by square root of 13. Okay, so suppose now we have a function that is described by some level curves, as shown here. How do we draw a vector showing the direction in which f increases most rapidly at a particular point? So we're asked to show when the direction where f increases most rapidly at the point 3, 5. So this up here is going to be 3, 5. We know that our vector, the direction in which our function increases most rapidly is given by the gradient vector. And we know that our gradient vector is orthogonal to our level curves. So that means this direction that I need to draw is orthogonal to our level curves. We see that the one to the right is 40, the one to the left is 60. So that means that our gradient vector, our direction of steepest ascent, needs to be pointing at right angles away from this level curve of 50 in the direction of the one at 60. Okay, so that is the direction in which f increases most rapidly. How about the second part then? So we're asked to draw a curve of steepest ascent starting at point 4 minus 3. So where's the point 4 minus 3? 4 minus 3 is down here. So how do we draw the curve of steepest ascent? So let's zoom in. Well, we know that we need to go at right angles to our level curves. So if we do this, we're going to get a series of steps. So we move orthogonal each time to our level curves, and eventually leading here towards the origin. So if we tried, if you imagine this was a mountain, if you wanted to take this path up here, this would be the curve of steepest ascent. This would be the hardest route to take up the mountain. This would be the shortest and steepest route up the mountain. So steepest ascent. Now what we've learned about functions of 2 variables applies to functions of more than 2 variables, as is the case pretty much for everything here. What we learn going from 1 variable to 2 variables is the biggest change. Going from 2 variables to 3 variables is essentially just an extension of what we've already learned. So if we have a function of more than 2 variables, for example here f is a function of x, y, and z, then all we need to do is just add on an extra component for our gradient vector, and our directional derivative is calculated in exactly the same way. Okay, so if we fill out this example, grad of f, x, y, z, is just going to be our partial with respect to x, our partial with respect to y, and our partial with respect to z. So in this case, we have e to the z, and x e to the z plus y. The second part, we're asked to find the directional derivative of f at a point 1, 1, 0 in the direction of v. So this vector here, 1, 2, minus 1. Note first of all that this is not a unit vector. So if we let u be our unit vector in the direction of v, then it's going to equal v over the length of v. And that's going to be 1 over the square root of 1 squared plus 2 squared plus minus 1 squared times by our vector v, which is 1, 2, minus 1. We're going to have 1 over root 6 times by our vector v, 1, 2, minus 1. I'll just leave the root 6 out the front so I'm not making things too messy here. So we have a unit vector in the direction of v. All we need to do now to work out du, our directional derivative of our function f at 1, 1, 0, is take the dot product of our gradient, which we've already calculated in general, grad f at 1, 1, 0, dotted with our unit vector u in the direction we want to go. So if we substitute 1, 1, 0 into our gradient vector, we're going to have 1, 0, 2. And we're dotting this with our u, so root 6 times by 1, 2, minus 1. So we just end up now with 1 over root 6 times by 1 plus 0 minus 2, so just doing our dot product. And then this simplifies to minus 1 over root 6. So this tells us then that if we start at 0.110 for our function, and we want to move in the direction of v, for every unit step I take in the direction of v, our function value decreases by 1 over root 6, and it decreases because this is a minus 1 over root 6. So you can think about whenever you're doing these directional derivatives that you are stood at some point, say on a hillside, and you have decided to walk in a particular direction. And at that point in time, you want to know for every unit step you take in that direction at that particular point, what is the change in height? So are you going uphill? Are you going downhill? And by how much? That only applies obviously at that point, because these are smooth surfaces. As you move along, the gradient will change. Okay, so this is an instantaneous change in height at that particular point. Okay, so today we've talked about the directional derivative and the gradient vector and some interpretations of what those mean and how we calculate these things. Okay, thanks very much. Bye.